Good morning, good afternoon, and good evening. This is a problem walkthrough for hydrostatic problem. What is hydrostatic? In Greek, hydro means water, and static, as we all know, it means something that is in stationary. Let's take a look at the question. A long solid cylinder of radius 8.8 meters hinged at point 8 is used as an automatic gate. When the water level reaches 5 meters, the gate opens by turning about the hinge at A. Determine the hydrostatic force acting on the cylinder and its line of action when the gate opens. So, as the water collects in this, let's call it a tube, it will have a force acting on the gate to push it up to open it. You may notice that we already have an FR right here, which is what we're looking for, but it's tilted at an angle. Why is that? We'll talk about that later. From the force pressure area equation, we know that pressure is equal to force divided by the area that is acting on. So the pressure and force is acting on the area and it's perpendicular to it. So we got F is equal to PA. But now we have a new unknown, which is P. How do we find P in the water? Well, the pressure in the water is defined by the water pressure equation, which P equal to density of the water, gravitational acceleration, depth. So the pressure of the water is height dependent. As it goes deeper, we have a higher P value. For this gate, we have infinite numbers of pressures at different magnitude that is acting on the gate. Also different directions. We could use an integral to calculate that, but also we could split them into two directions. Let's call it area X and area Y. So if we find the pressures that is acting on AX and the pressures that are acting on the AY, the product of these two forces would be equal to the hydrostatic force that we're looking for. Let's first take a look at the pressure that is acting on the AX. As we all know that pressure is height dependent, so as we go deeper, we got a higher p-value. So we could use a integral again to calculate that, but we could also use superposition, which means moving some of these forces around to here, and then we got a evenly distributed load. And the centroid of this evenly distributed load is just the middle point. And the pressure that is acting onto the centroid is the average pressure. The average pressure is equal to rho GH, and the H here is the middle point of AX, which is this length, is 0.8 meters, so the centroid would be 0.8 divided by 2. And do keep in mind that it's also 4.2 meters deep, so plus 4.2, and this would be our pressure. But we're looking for forces, so we are going to multiply that. Let's call it Fx. Fx would equal to P average times area. What is area? Well, the area here would be the height times how deep it goes into the page. Here it says per meter's length. So we're assuming that for this problem, we're going 1 meters into the page. So it will be just height times width. That's the area. So now we have pressure, we have area. We can start calculating for the force that is acting in the horizontal direction, which is 36.1 kilonewtons. How about the vertical forces that are acting on AY? We know that the water is exerting pressure on the surface that is touching. So we know that the pressure will be on AY as well, which is this length. That's it. And it's 5 meters deep. At every point on this area, we have the same pressure. So for the pressure, let's call it Py, would equal to rho GH. Rho G are the same, and the H, which is the depth, it will be just 5 meters times 5. Still, we're looking for forces. Let's call it Fy would equal to Py, the pressure times area again. So rho G times 5, that's our pressure, times area. The area right here is 0.8. It's the same as the radius of this circle. 0.8 meters, and it's 1 meters into the page. So 0.8 multiplied by 1, that's our area, and we found 39.2 kilonewtons. So Fy is the force that exerted by the water onto the ground, onto this area. And in return, the ground will give a supportive force back to the water. Let's call it Fn. So Fy here would equal to Fn. That's our force in y direction. But are we done yet? Well, not really, because the water in this area has a weight as well. So the actual net force in y direction, Fy net, is equal to Fn is going upward minus opposite direction is W. Now we have Fn, but not W yet. So let's look for the weight of this water. We know that the weight is equal to mass times gravitational acceleration, but still we don't know about the mass. So we're gonna convert it to something else. We know that the density is equal to mass divided by volume. Can we use that? Oh yeah, we know the density of the water, and if we know the volume of the water, times that by G, we'll be able to find the mass of the water. The weight of the water. We'll be able to find the weight of the water. So what is the volume of this area? Still, we could use superposition. We can make it a square minus the quarter circle. So we have the area of the water times that by 1 meters into the page. We will be able to find the volume of it. So the area of this water would be we know this is 0.8. That's the radius of the circle. And here is our square. It would be 0.8 squared, that's the area of this square, minus the area of this quarter circle, radius square pi divided by 4. So this will be the area of the water. If we multiply that by 1 meters deep into the page, so this would be the volume of the water. And we're going to plug that into the equation. We'll be able to find that equal to 1.3 kilonewtons. Alright, so now we have Fn, we have W now. The Fnet, Fynet would equal to 37.9 kilonewtons. Now we have found Fx and we found Fy net. Now we should be able to calculate the product of this vector. So the resultant force would be just Fr. Let's use the same symbol as the question. According to Pythagorean theorem, we found Fr, which is equal to 52.3 kilonewtons. So that would be the hydrostatic force that is acting on the cylinder. We're also looking for the line of action by this force to the gate. For this evenly made perfect cylinder, whatever the resultant force that we have, whatever the location it has, it will be pointing to the centroid. This is A. So to define the line of action, we will just need to figure out theta is Fr. Just like what we have on this graph. So theta, it will be simply solved by tangent Fy net divided by Fx. And we have theta equal to 46.4 degrees. We are also looking for the weight of the cylinder when this gate is just about to open. How do we find that? Since the gate is rotating about A, we know that the sum of the movement at A equals to 0. That way we have the system in stationary. The moment developed by the weight of the cylinder is the weight of the cylinder times the distance to the center of the moment, which is 0.8 meters. And since the weight is acting downward, it will create a clockwise movement about A. And we are going to define clockwise as negative. How about the resultant force by the water? And we know Fr is going this direction about A, thus it will create a counterclockwise movement. So that would be positive. It would be plus Fr times the distance of the Fr to A, which would be the length of this. How can we find that? Well, we already know theta and we know the radius. So we know this, we know this. With sine, we should be able to calculate this length. It will be just radius times sine theta. You may wonder, how about the force that is acting from the ground? Well, we already know that the gate is about to open. So this force is no longer exist. So this will be the sum of the moment we have about point A. And solve this equation we will be able to find W is equal to 37.9 kilonewtons. And this will be the weight of the cylinder. Now we have found everything. Here's the weight. Here's the resultant force and its line of action. Thank you.